Okay, and now for a field pattern test on my new beam antenna, which is vertical phased array. Here we go.
Frequency mode.
VK, 3 VK, testing on this frequency. So I'm transmitting on low power on that little UV, whatever it is, and I'm just going to run over here, quite a few wavelengths away, and the antenna's spinning. I've got my field strength meter with the antenna not extended. So there's the front, right? That's the side. You'll see this is a very sharp lobe. I'll move across a bit. That's the back. Now this is the side. We're coming to front. Look at that sharp lobe. Side. Back. Side. Front. I'll try and keep this all in view, right? So the back there. Bang on the side. Coming around front. Side, back, side, front. I'll let it keep going and slow down so you can get more detailed view of the front lobe as it slows. So coming around to the front now, bang on the front, off the side, onto the full-on side, and notice how I've done a really nice job at killing the rear lobes. And the front, whoa, that's low power on that little radio too, on 146 megahertz. And I notice I haven't got my telescopic antenna extended out on this little thing either. So, right, front, you little ripper. And the SWR is rather nice too, and this is just first draft of this one. It's not my very first attempt. My very first attempt is down here. It was great. The only thing is it was such a flimsy build, so I've just rebuilt for convenience. I'll just stop the transmitter and explain a little more. VK3, VKE, test complete. Okay, now this is wider than it has to be. This is just the rods. Because I reuse things, I didn't want to cut them down. So this is the actual end width of the antenna. So left to right, it's actually only a half wavelength wide, and between the front two elements and the center two elements, that's a half wave. And then basically, it's quite interesting. Without this left and right reflector elements, it did have a beautiful null on the rear, but it did have some lobes coming out the rear side. So I've added these extra reflector elements. Now, the design concept is this particular furthest back reflector element is exactly a half wavelength in direct distance from this element here and also this element out here. But the interesting thing is, of course, this element and this element are behaving coherently with this and this, because these are 180 degrees out of phase, but they're also half a wave apart. So in this path, they're coherent, but of course, this path, them both being opposite, they're self-canceling. They cancel each other. But not only that, because these two are the same as each other, and these two are the other phase, even from there to there, they cancel each other. So it's massive, like double whammy cancellation to the sides. But as for so without this back section, it would be very bidirectional, sort of that way and that way. And having this one killed the rear lobe, but this one then, and the other side, how I've done that, is this one is exactly half a wavelength from the opposing side element. And this one is exactly half a wavelength from that opposing side element. And this one is half a wavelength from both. So why it works this way, these are not actually reflectors. We call them reflectors. They could try to radiate, but the thing is, that's what they're trying to do, but the radiation that they create is less coherent with what's going on at the front. So just like with DC and the resistance and the least path of resistance, with antennas, not just within the circuits, we have to consider the least path of impedance. So this ends up being ignored, and the energy just comes out the easiest way, because there's not complete cancellations, but some sort of minor cancellations when it comes to interacting with these from there, which are also further away. So it's just much easier for it to then throw all of its energy out that end. It's very hard to explain, but hopefully that kind of makes some sense. So there she is, and I am super impressed. Let's have one more look at that ratio. Here we go.
Frequency mode.
VK3 VKE testing on this frequency, and that rhymes, doesn't it? Okay, so I'll just give it a quick spin. It's probably wobbling a bit, and get my trusty field strength meter, which should be front. Yep, there's front and side, rear, get that in view, side, and front. So sharp, isn't it? Beautiful. Off to the side, and it's just about to stop. It's not quite going to make it around to the rear. So not quite making it around. It's going to come back the other way now. But I am utterly stoked that I succeeded. I've been racking my brain for days on end, so it's not just an overnight thing. But yeah, it's a success. And there you go, there's the front. And it's nothing like a Yagi in another sense, by the way, because, you know, a Yagi would expect, you know, the front element here to be two sides of the circuit, you know, two sides of the system like a dipole. But this isn't. These are both on the same phase. These operate together. And these two are on the opposite phase to that. So if anything, it's like we're looking at a dipole side on here, and from the top view, and a dipole side on here. But the fact is that they've both got their vertical sections. So that means like a dipole, let's say, when current's driving this way, it's also driving this way. So we have coherence on a dipole like that. But if you imagine that path of the current, because they're opposite phases, when this one is coming this way, it's coming down. When this one's coming this way, it's coming up. So from a vertical perspective, we're back to a cancelled, like on a balanced line, from the side view. But of course, from the front view, these two are in the same phase. So they're two constructive waves in the forward, and also the ones behind them are constructive with them, because by the time they get there, it's in phase. If you follow my gist. 7-3, and thanks for watching.